2, 1. Great. Okay. Welcome everyone. We will give some time to let people populate into the audience. All right. We've got some people coming in now. Wonderful. Okay. I hope that all is well. Let me know in the chat where you are listening from. Did you find us on Twitter? Are you on YouTube? Are you on our Facebook? Please follow us on LinkedIn so that you can find us there for our live monthly sessions. Um, my name is Dr. Raven Baxter. I'm Director of Science Communication at the Cohen Center for Recovery from Complex Chronic Illness, also known as CoRE. And we are a new center at the Icahn School of Medicine at Mount Sinai Hospital in New York City. And we have a mission of advancing treatment and knowledge of complex chronic illness. So you're joining us for our third live knowledge session, and we host these monthly. So make sure that you're following us and signing up for our notifications so that you don't miss it. But of course, you can always watch the replay on our YouTube channel. Just type in CoRE Sinai, CoReSinai, and you can find us there. Um, and but of course, if you join us live, you'll have the opportunity to ask us questions and perhaps get some answers live as well. So we encourage you to join us if you can. So today we will be talking about pathogen reactivation, which is a potential driver of complex chronic illness and specifically post-acute infection syndromes. And so today we're going to be talking about the foundation of what that is, and also talking about some of the things that we're doing at CoRE to research pathogen reactivation and also potentially treat pathogen reactivation. But with that being said, the information in this session that we provide is purely for educational purposes. We won't be providing any medical advice. So with that said, we're also very excited to share what we do know and invite you to learn with us about the science behind the chronic illnesses that impact people's lives. So I am joined today by Doctors David Petrino and Amy Proal. David is the National Family Director of CoRE, and Amy is the Scientific Director of CoRE and also President of the Polybio Research Foundation. So I'm thrilled to be chatting with you both today. Let's jump right into pathogen reactivation. And of course, again, to the audience, if you have any questions, don't hesitate to put them in the chat. We will be monitoring that as we go. Amy, would you like to start by explaining what pathogen reactivation is?
Sure. So over the course of our lives, and honestly, even in the womb, so sometimes as early as when a baby literally is, gestation period in the womb, they're seeded with pathogens. And then over the course of our lives, we acquire more pathogens as we just go about our lives, depending on what we eat, who we interact with, where we travel, what we do, right? And these pathogens can span viruses, which include the DNA viruses. For example, those are herpes viruses, are prime examples of DNA viruses. Those include the Epstein-Barr virus, human herpes virus 6, human herpes virus 7, cytomegalovirus. Actually, increasingly huge players in chronic disease processes, but actually acquired and harbored by the majority of the human population. So this is the thing, is that well over 95% of people, and in fact, I'm sure all of us here, have at least one herpes virus. For example, cytomegalovirus or Epstein-Barr or herpes virus 1 or 2. The thing is that these viruses, which are part of some of the pathogens that we can acquire over our lifetimes, are normally kept in check by our immune systems. So they're kept in a dormant state, or sometimes it's called a latent state, depending on the pathogen, where really, despite the fact that they can actually drive a lot of disease causing and pathogenic activity, they're kept down by our immune systems so that they cannot do that. And they're kept in this state of latency or dormancy. But under certain conditions, under conditions of immunosuppression, under conditions of immune dysregulation, potentially under conditions in which someone gets another infection and that infection disables or throws off or dysregulates the immune response for a period of time, these more dormant pathogens can activate and change their activities in ways in which they can drive many different forms of disease. And when they do activate, key is that they change their activity. They change, for example, the proteins that they produce. So if you're a virus, as we all know, for example, the SARS-CoV-2 virus makes the spike protein, right? It actually makes other proteins, but we're all pretty familiar with spike, right? The spike is actually part, the protein from the virus that causes a lot of damage and problems in people infected with the virus, right? So all viruses have proteins, and essentially the proteins are, in a way, the weapons that they use to start to dysregulate the signaling of our human genetic pathways, the signaling of our mitochondria, all kinds of problems, even the epigenetic environment, which is basically the way that our code of DNA is sort of methylated and interpreted in the human body. So there's just a massive effect that can happen. So to summarize, people acquire bacterial, viral, fungal pathogens over the course of their life, and often they're in a dormant, contained form. And yet there are conditions in which they can activate, and that's basically what we're going to talk about today. What happens, what makes them activate, and what can they do when they activate. But that's kind of the scenario.
Yeah, and so this is a really fascinating topic because it has the potential to impact almost every single one of us, considering 90+% of people have latent pathogens in their bodies. So let's talk about the disease process. How can pathogen reactivation serve as a fundamental cause of complex chronic illness?
Yeah, David, do you want to talk a little bit? I mean, I can also just keep going. One of my favorite topics. Should I?
I'm not going to take your favorite topic away from you. You got to go. I can talk about what we're doing at CoRE after.
Yeah, fair enough. All right. Well, look. So, I mentioned that if a pathogen is in a dormant state, it usually isn't creating proteins, and it's usually not replicating and infecting new sites, right? It's contained. But if a pathogen is able to reactivate, it's able to often produce new proteins. And sometimes those proteins can have a true impact on disease. And I just want to give, let's say, one example that comes to mind. So Epstein-Barr virus, which is honestly harbored by a good number of people, people can have Epstein-Barr virus and be fine, given in the moment, or seem fine. But there's, a couple or multiple studies, if you really look through the literature, now connecting Epstein-Barr virus to multiple sclerosis directly. And some of those studies show that the proteins that Epstein-Barr virus is able to create when it becomes more active in someone can interfere and confuse our human signaling in ways that allows our immune system to, for example, target our human tissue via, for example, a process called molecular mimicry. A good example, though, one of my favorite examples of Epstein-Barr virus proteins, when it's in a more active form, being able to drive disease, is actually a paper in which a team looked at a protein created by Epstein-Barr virus called EBNA1. And there are risk genes that have been associated with human autoimmune diseases. So, for example, I mentioned multiple sclerosis, but let's say also lupus or even diabetes. And there are teams that have basically gone through our human genes and understood that sometimes certain genetic combinations of variants in people's genomes confer more of a risk towards the development of, let's say, a condition like lupus. Well, this team showed that the EBNA2 protein created by Epstein-Barr virus can directly bind, gets into the center of our human cells. It accesses our DNA, And then it directly binds into those areas of the genome that code for lupus risk. And there it amplifies the risk. So for example, this team found that EBNA2 protein created by Epstein-Barr virus bound into 50% of the risk genes that control lupus. And it just, these viruses, they basically, in a sense, are hackers. Once they're active, their proteins can directly access our own genetic material and literally amp up the risk for chronic disease that we develop. And that's just one example of what they can do when they're active, right? So the thing is, we actually, in my opinion, need to start taking a lot of these viruses and pathogens more seriously. One of the issues that has gotten in the way of that happening is the fact that all of us often harbor them right? So for a while, and still you'll hear this out there, people will say, oh, well, if a lot of people have Epstein-Barr virus, then does it really matter? And the key problem there is that it can act differently. Like it can be, as I said, in a dormant form where it's not creating proteins and it's not replicating or it's not infecting new nerves or tissue in one person. And in a second person, it can be changing its activity, creating proteins or doing something different in a way that can drive disease. So the question really isn't, does someone have, the question is, does someone have the virus or not? That's the first thing we want to know. But we always have to ask a second question, which is, what is the virus doing in someone? That's really where the key comes into, if it's driving disease processes or not, and if we really need to make an extra effort to go after it and hopefully try to counter its activity, maybe get it back down into at least that latent state where it can cause less problems, right? So that's a lot of what the research we're working on in CoRE Polybio is better understanding those mechanisms that are specific to a virus when it becomes more active and becomes involved in a disease state and changes what it's doing in one person in which it's driving symptoms or problems versus in another person, even though they have it where it's not, right? So, and last, and then David can speak to this maybe a little bit clinically, that does make it hard to assess these viruses in patients in the clinic, though, because the testing that we have, let's say even at CoRE, honestly, that we can access from labs like Quest Diagnostics or LabCorp that many of you are familiar with, which are what we can order from that are covered by insurance. Those labs really can't tell us much about that second question, which is, what's the virus doing? They can allude to if a person has the virus. And a lot of times they actually just do this based on characterizing if someone has an antibody response towards the virus, as opposed to even identifying the virus itself, which can be a little wonky. So we don't have the tools in the clinic sometimes to be able to know how the viruses have potentially changed their activity. We don't have ways to measure that. And so we're stuck in a clinical setting, still often having to guess, right? Which is why it's really important that a lot of the research we're doing, for example, just understanding these multiple sclerosis connection studies tied to mimicry of viral proteins or the virus proteins, like I described, acting as transcription factors that can up risk, all of that understanding that's in science labs right now needs to translate better into the development of more innovative clinical tools that allow us to understand viral activity better, in addition to just if it's there or not.
Thank you, Amy. And so in talking about pathogen reactivation, should we just be worrying about viruses, or are other organisms are likely at play here, right? I would like to talk about the other organisms.
Yeah, no, we definitely should be worried about many others. And viruses obviously there's plenty of virus examples that we're worried about. We're even worried about SARS-CoV-2 persistence. Even SARS-CoV-2 appears capable of persistence and in tissue in patients for years, months. So it's a new player in the game of viruses that can almost certainly contribute to disease in a chronic capacity. But bacteria fungi are also, and parasites are actually big players in the pathogens that can reactivate or activate and drive chronic disease processes. And some of the most straightforward bacteria that are players in cases of complex chronic disease are actually the tick-borne, vector-borne pathogens. These are pathogens that are either, it's like what it sounds like, acquired via a tick, but actually can be acquired by other vectors. I think this really isn't understood enough, that it's normally, there are pathogens, bacterial pathogens, especially Babesia and Bartonella, both of which are pathogens that infect the blood vessels, actually sometimes directly infect and even persist in red blood cells, but can drive a wide range. Also, they can infect nerves and persist in a lot of other sites. So they can drive a lot of chronic type symptoms, including vasculature issues, including problems with blood vessels, but also even cognitive or neuropsychiatric symptoms. Those bacteria can be acquired often via just a flea or a cat who has fleas that can contain Bartonella, or a spider bite that actually might carry these pathogens. And so there's a lot of ways in which, for example, Babesia and Bartonella can actually be transmitted and end up in someone's body, again, in a way that maybe at first sometimes doesn't manifest in overt symptoms or disease. But again, if the person starts to suffer from other problems, or if the immune system goes down for other reasons, they can, again, definitely change their activity or infect new body sites in a way that can be really problematic. And there was actually a case history recently that showed that a patient with a long COVID diagnosis, who had symptoms obviously began after SARS-CoV-2 infection, was tested for Bartonella, one of these vector-borne pathogens, and was found to be positive for Bartonella. And when they treated the Bartonella, the symptoms of what they were calling long COVID went away. And in that sense, what seemed to have happened in that patient was the SARS-CoV-2 virus came in, it probably knocked down the immune system in a way that allowed Bartonella that the person had, that they didn't really realize they had, to manifest more as a bacterial organism, replicate more, infect more blood vessels, more nerves, potentially drive more symptoms. And that was, in that particular patient, the root of their problem. So, we have this bacterial component, and there's other bacteria that can play into this: mycobacteria, brucella, Q fever that people sometimes get. There's a lot of bacterial pathogens that are acquired and can be included in the players of this game. And last I'll mention parasites, because there's one that's such a compelling example of a pathogen that a huge amount of the human population harbors, that we blow off in ways that amazes me. And that pathogen is Toxoplasma. It's a parasite that infects the central nervous system and actually persists in the brain. And the stats are that I think between 30 to 60% of the global population harbor latent Toxoplasma in their central nervous system. That, again, in a apparent dormant state, right? I think 11% of US Americans are thought to harbor latent Toxoplasma. And this is a parasite that, when it is active and when it is in a disease-driving capacity, if you infect rats with it, or mice, and they're around cats, the parasite modulates the neuropsych of, brain capacity of the mice, so that they're actually no longer afraid of the cats and they don't run away. That's how manipulative this parasite is to cognition, right? And so I just, in the scheme of chronic disease, we have a lot of these pathogens, let's say Toxoplasma, that are persisting in people latently, often in the brain. And then we have conditions of unknown cause, like schizophrenia, or I don't know, other neuropsychiatric conditions. And I think that the Venn diagram of those pathogens and those, unknown illnesses really needs to overlap, and is starting to overlap more in research, where these latent pathogens capable of driving neuropsychiatric symptoms, at least may be contributors to these, neuropsychiatric or other, neurological conditions or symptoms that become part of people's chronic disease cases across the board.
And so and just to recap, because we've had about 400 people join since you started talking, we're talking about pathogen reactivation. And just to simplify things, because I think we're speaking to a very broad audience, pathogens are disease-causing organisms. We have, our human cells, our people cells, and then we have other cells and things living in our bodies. Also viruses that can infect us or live within us in sort of like a relationship, like a natural relationship with our people cells. And so, Amy, I want to talk about like what can cause the reactivation itself. Like, can it be stress induced? I'm sure it can be disruptions. Various disruptions in your body can cause these other things in our bodies that aren't our own to start waking up and saying, "Oh, I can do some stuff in here. Let's wreak some havoc, or let's cause some dysfunction."
Yes. The simplest and most straightforward reason is that the immune system suffers in some way. I mean, these pathogens, the way that we keep them down is because our immune systems from, the innate immune system, which is, our more basic cells like our neutrophils or natural killer, they're aware of them, they're keeping them in check. And then our T cells, our B cells are also, making antibodies or responding to them in a way that recognizes their presence in the body and essentially like knocks them down if they try to do something. So if you disable the immune system, either that innate branch or the adaptive T cell, B cell type cell branch, you give these pathogens a way to kind of, act up in a way that they weren't doing before. And so there's, so many ways, unfortunately, that we disable the immune system. I think that one for sure is that environmental exposures are actually a big problem. There are people, for example, who have lived in a moldy room. They didn't realize it. And mold the mycotoxins can compromise the immune system really badly. And then after they're in the moldy room for a while, that's a great atmosphere in which the pathogens can take advantage of the immune system getting muted by the mold exposure to be able to potentially reactivate and be problems, right? So you have other environmental toxins or issues, which again goes to the fact that we really do as a world need to think about keeping our environment, keeping microplastics out of our lives. And it all matters because they affect the immune system negatively in a way that is great for these pathogens, right? Second, though, stress is definitely a factor. The stress actually has an impact on the immune system. There are studies that show this, right? Like there's changes in hormonal and endocrine type signaling associated with stress that are directly connected to the immune response. So a stressful event, and that could even be, for example, a pregnancy or just an accident, a really bad concussion. That is another event that can cause the immune system to go down or even have to become distracted. Let's say you have an injury, like a concussion. The immune system has to go in and try to deal with that injury, try to repair all that. Again, it's in a sense distracted with this other problem that almost leaves it less able to monitor the viruses or other bacterial organisms that it was otherwise containing, right? And then another way, that the immune system can go down is another infection, right? So we see this with SARS-CoV-2. For example, there are multiple teams that have shown that patients with long COVID seem to have reactivated Epstein-Barr virus. And that is very likely because when they got infected with the SARS-CoV-2 virus, the virus has multiple proteins that downregulate the immune response to let it better infect you. Some of those proteins are called interferons, and those interferons are really important in a good response to viral infection. And SARS-CoV-2 knocks down interferon signaling. I mean, it's smart, right? The virus knocks down the proteins and the response that would otherwise come after it, And thus, when those interferons are knocked down, any other virus in the body goes, whoa, hold on, interferon signaling is knocked down in this person right now. I'm going to reactivate too, And so I'd say those are just a couple examples of events that can affect the immune system chemical exposures, toxic exposures, stressful events, trauma, injury, pregnancy, other infections. And a lot of times you'll see in patients who develop complex chronic illness that if you ask them about their history, they report having these different exposures or infections or other issues in their cases. And those potentially, I refer to those as hits. In other words, they have, an infection, they have got a concussion, they, were exposed to mold. That those different hits definitely, in a sense, can successively potentially disable the immune system or throw off other signaling in the body in a way that makes it increasingly easier for pathogens that were previously latent to activate and become players in driving chronic disease processes.
Amy, thank you for explaining that. And we have some comments from the people watching who find this fascinating. I agree. So another question for you is, are these hits always obvious? Like, if you're in a moldy room, like, is it going to take you keeling over and passing out, or is having some type of obvious reaction to your environment? Is that what it takes to trigger like a default in your immune system, or could it be very subtle and something that you may not even notice is happening to you?
See, that's a great question. And I think that they can be subtle, and that's what's worrisome. I think that's one of the reasons that, our Polybio and even at CoRE, we're focused in part in long COVID on SARS-CoV-2 persistence, which is the fact that some people just don't seem to be clearing the virus after they get it. The reason is because it is really disconcerting that you could have potentially a mild or maybe even an asymptomatic infection. Again, it doesn't seem like this big hit in the moment, but the virus might persist, let's say, in a small amount in what we call a reservoir in the lining of your gut, in the tissue of your gut, or maybe in your lymph nodes. It just doesn't clear. And then over time, though, depending, if the immune system still isn't in great shape or if there's other problems, it becomes, it could potentially, what it can do in terms of driving disease, it could do slowly over time. In other words, you could manifest disease gradually, right? And so that's the thing is, you might have an asymptomatic infection, but if you don't clear it, and that can happen with, Bartonella, like I mentioned before. There are people who test positive for Bartonella antibodies that don't seem to have symptoms. So maybe you can have it and be all right for a bit, right? But what about 5 years from now, 10 years from now? Is it going to do something then, right? Same with the mold exposure. No, this is the worrisome part, is that, people feel bad for a lot of reasons, and our society normalizes feeling bad to a point. It's like, oh man, I'm just having a bad day. This, it's all like we see with COVID. Hey, going to work anyway, this. So we're not really conscious a lot of times in our lives to say, I'm not sure, I don't feel good in this room or whatever it is. We're basically just running around trying to get things done, hoping for the best. And we're not educated a lot on the fact that there can be things like mold or other chemicals or whatever, heavy metals that are problematic. We're not told about this very often. So sometimes when people aren't feeling great or whatever, they think, oh, this is a part of life or whatever, right? And they don't even realize that it's probably, a hit that's part of their case.
That's such a good point. I mean, honestly, just a relatable topic, because I feel like the moment I finished grad school and I wasn't bombarded with this constant stress of deadlines and expectations and requirements, I was able to pay attention to how I actually felt on a day-to-day basis. And I'm like, oh, hey, I'm getting kind of congested when I go into the basement. And like, hey, I might actually be allergic to that tree in the backyard that I like to sit under all the time and work under. But now that I'm not working, I'm like, oh, I might have an allergy. So that is actually super important. And I think, just touching on that societal note you hit on it, I do wish that we had, as a society, more opportunities to kind of slow down and pay attention to what's going on with our bodies and what's in our environment. So thank you. And want to just remind all 700 of you who are watching that you can ask us questions. We are monitoring the chat. I can see your comments on YouTube. hello to YouTube, hello to people on Twitter. If you're watching on Facebook, let us know where you're watching from. Please follow us on LinkedIn. We need some followers on LinkedIn so that we can stream there as well. So please go there. And yes, please leave your questions in the chat. One of the questions that I think, naturally I hear from people is how do we find this, right? And I know that the methods that we have for testing they're not where they need to be so that we can find every single latent pathogen or even identify things before they reactivate. And so what is the status of testing and for pathogen reactivation?
Yeah, of course. I mean, it's kind of $1 million question. And, and David, I'll just keep going. I mean, as David knows, like the other day, like someone actually termed the way I look at chronic disease, like pro-all pathogenism. And I think that that's reasonable. Like I have a big focus on this. So I'll just keep going. I think that, look, there's a couple issues with trying to understand if someone has a pathogen in them, number one. And then the second thing I mentioned before, which is what is it doing potentially to drive disease? What kind of proteins is this expressing? What is it doing, in terms of maybe affecting mitochondria or other factors? The first is just even understanding if it's there. The problem that we have is that the vast majority of our medical tests are based on blood. So obviously we get blood drawn. In a funny way, medicine thinks that everything that we're supposed to know if someone's sick is in this blood sample. I mean, it's always amazing to me when you see doctors who, have basically run blood work on someone, it comes back normal, and then they go, oh, there's nothing wrong with you. I mean, it's hilarious because what's in blood is obviously, doesn't necessarily have to reflect what's in the entire rest of the human body. In other tissues, certainly what's in the brain. So blood can only tell us so much. And that's really key here because pathogens like tissue, that's where they hide out best. I mean, if you are a pathogen, it's not really that smart to just be in the blood. If you're free floating around in the blood, you are going to get noticed. That's where immune cells are. You're going to get targeted. So of course they hide. I mean, they don't just stay there where we are going to easily find them with tests. They go hide either deeper in tissues, like I mentioned, for example, the gut lining or other tissues of the person's body, or they potentially hide inside host cells. So for example, our white blood cells, macrophage, or sometimes monocytes, depending on their stage, are a known almost Trojan horse mechanism by which a lot of pathogens, so macrophage cells they're white blood cells that are supposed to engulf and kill pathogens. But many pathogens have evolved mechanisms by which, even when the macrophage tries to engulf them, they create, compounds or proteins that help them combat that attack, and they stay alive. And then they make the macrophage their home. They Trojan horse into it, right? And so they actually survive inside the cells of our immune system that would otherwise kill them, which is really a win on their part, right? So you have host cells as definite, sites in which these pathogens hang out, all of which are harder to get on blood tests, and so what we do, what's really happening when almost all of us go to the clinic and someone tries to understand if we have a virus, they're taking blood and they're actually not even looking for the pathogen itself. They're not looking for the backbone of the pathogen. If it's an RNA virus, it has an RNA backbone. If it's a DNA virus, it's its DNA backbone. If it's bacteria, it's its actual genome. We can find those with tools. They're not even doing that. What they're trying to do, they don't really have the tools for that, is the truth, in the clinic. They use antibody testing. So what they do is hope that our immune systems have recognized any pathogens that might be in us and have created an antibody response, an immune response. We all know antibodies because of the vaccines, and we're supposed to be creating antibodies when, we're infected with something or when we're given a vaccine. Those antibodies should form in response to a pathogen. And thus the hope is that if you measure an antibody, then you can sort of say, we use that to infer that the person has the pathogen. The problem with that, though, is that antibodies can be long lasting. So you could be exposed to a pathogen. For example, let's say Bartonella, that bacteria again. Maybe you got it and then you created antibodies to it. So now you have Bartonella antibodies to this strain of Bartonella. But then maybe your immune system actually cleared it, got rid of it. The antibody remains, though, maybe. So the problem is when we measure the antibody, we can't confidently say that we know it means that the pathogen is still there, because the antibody could sort of outlive the potential clearance of the pathogen. And that's why, it just tells us that the person was once exposed. Like, yes, you have come in contact with Bartonella, or you have come in contact with Epstein-Barr virus, but it does not tell us confidently if it's still in you. That's real lack of information, right? The second problem is that every pathogen, like I've been saying, disables the immune system as part of the way that it drives disease, or especially as part of how it persists. And a lot of pathogens disable antibody responses, because think about it, like if antibodies are supposed to be recognizing you and targeting you, if you can find a way to make proteins that disable the antibody responses, then you can hide out more. So the problem is that people who might have some of the most serious infection or non-cleared persistent infection, their immune system, the pathogen might be actually down regulating their ability to correctly create an antibody response to the pathogen's presence. Thus, if we're looking on a clinical test for the antibody, it hasn't been created because of the pathogen's, crafty, down regulation. So you could, in other words, it's not reliable because pathogens affect the immune response and potentially antibody production. So the majority, though, of clinical tests are antibody-based. So if you go now to get tested for Epstein-Barr virus, your doctor is likely running what's called, IgG or an IgM antibody test, that basically means that you created antibodies to certain Epstein-Barr virus proteins. And it's okay. It's a start. At least we know that you encountered this virus. But and based sometimes off the titers of those antibodies, there are doctors, because they've treated a lot of patients over the years, if the antibody titer is a bit higher, they decide that they're going to treat, but it's an imperfect measurement. And that's a lot of where we stand in the clinic right now. The dream and the goal that we must achieve is that we actually have to develop technologies that find the pathogens themselves more, or the products that pathogens create. Products that wouldn't be there unless the pathogen was there. I mean, so for example, with SARS-CoV-2 and SARS-CoV-2 persistence, there are teams that are creating really, really sensitive, and by that sensitive, I mean tools that can find very, very tiny amounts of protein to find SARS-CoV-2 proteins, for example, in the blood of patients with long COVID. And multiple teams have found, spike, or in some cases N protein, but largely spike or S1 in long COVID blood up to 14 months or more after initial illness. And the idea, which we think is happening, is that the patient probably still has the virus in their tissue, and that these little bits of spike protein are budding off the virus, potentially in a little vesicle called an exosome, and then getting into the blood where we can measure them in small amounts, right? And I do think that it's an intelligent type of testing to pursue, because if the pathogens are hidden in tissue, and that's where their genetic material sometimes is, but their proteins, because the proteins are what they're using to drive disease more, leak out or are more likely to end up in blood, well, let's measure them. And every pathogen creates proteins. So if we're able to take some of these newer technologies, for example, some of the groups bringing more sensitive technologies into the SARS-CoV-2 proteins, keep iterating those into the proteins created by other viral or bacterial or fungal pathogens, maybe we can begin to pick up on small amounts of protein that can help us infer infection better, right? The other thing is that we can also potentially use tools that allow us to find the genetic material of the virus inside host cells. So, for example, there's some techniques, for example, like a digital transcriptomic techniques that's being used by a team in Belgium right now that we think might be capturing SARS-CoV-2 persistent RNA in cells like platelets in people's blood. And that's a good strategy. Maybe we can get the genetic material of a persistent organism from a host cell, but again, that requires a certain level of technology innovation. And last, because pathogens are often in tissue, one thing that we're working on is if we're able to get tissue biopsies from patients, which is, the consideration that might happen more in the clinic if needed, we're working on techniques where we can understand the microbial, viral, and fungal content of those samples. The one that we've been working on with the team at the J. Craig Venter Institute for a long time is metatranscriptomics. And what that allows you to do, if you do it right, is to pull all the genetic material out of a tissue sample, then remove from that genetic material what is associated with our human genes, which is a lot of what's in the sample. Take that out, take the human out of the sample. And then what remains is non-human. It's either viral, but it's something non-human. And then you use computers to map the sequences of that genetic material to the backbone genomes of different pathogens. And then you can kind of say, these are all the different pathogens in a sample. That is underway. We're doing that. The question is, how rapidly can we move this kind of testing into a clinical setting?
Thank you, Amy. Yes, I want to start addressing some of the questions that we have in the chat. Prefacing by saying we have people from all areas of expertise. So let's address this question. How do you increase the immune system in the lungs?
I know. I mean, it's a good question. So
I can probably
David, jump in
here. Yeah, because I want to point out, Barry. I noticed the questions that Barry and comments that Barry was making in the chat, and it seems like Barry is seeing MAC infection, and also Katie, hi Katie, is also experiencing MAC infection. Mm-hmm. So to start off, just with a brief introduction to some of these topics, as Amy mentioned, we're really
Did we lose David?
I think so.
Okay.
We're really doing something. Let me see if you can. Just test it. Let's see if he gets back on. Should I take another question in the meantime?
Sure. Kirsten asked, would a course of steroids be beneficial or detrimental with pathogen persistence or reactivation, especially with herpes viruses?
It's a great question. Technically, since pathogens can take advantage already if the immune system is suppressed or not in good shape to reactivate, steroids, which knock down the immune system further, are not necessarily the best idea, at least over the long term, though. That's the thing. There are drugs where, people with autoimmune conditions that might have increasingly an infectious component to them are put on really long courses of steroids or immunosuppressive drugs for life, right? That is probably not the best path towards immune control. That being said, in some cases, people have a pretty bad reactivation of a pathogen. So for example, let's say shingles, right? It's a herpes virus and, people will reactivate and get this like a rash from it all over their bodies. It's extremely painful. In some of those cases where that pathogen reactivation is really profound and strong, just in a given moment, in that shorter term period, it might make sense to use some steroids to take it down a bit more, right? So it kind of depends on the severity of the reactivation, but I don't think that long-term steroid use or immunosuppressive drug use is really great for this kind of patient population.
Wonderful. And
David's back. All right.
We got you back. So let's talk about these MAC infection.
Yeah. So my wife and I really took the best time to drop out after being on for so long with no issue, but here I am on cellular.
Okay.
So, I want to start off, thank you, Amy, for saying so much amazing stuff. And I really want to echo some of the work that Amy was talking about in terms of, I don't know why, and I don't know where this decision was made, but at some point in medical science, we kind of just thought, okay, well, bacteria and viruses persisting in the body aren't such a big deal. And also, we're going to trust entirely what our blood tests tell us, as opposed to going and looking for it in the tissue. Now, think about any other field and tell me if that is acceptable. When, prior to working in long COVID, a lot of the work I did was in stroke. You don't look for evidence of an aneurysm or a stroke in blood. You scan the brain and you look for evidence in the brain. You don't look for, and again, to preface, of course you can do quick screens in blood tests, but if you're looking for cancer and you suspect that somebody has lung cancer or kidney cancer or cancer in the brain, you don't do blood tests. You image and you look for you biopsy and you look for evidence of cancerous material. This is a level of evidence that we need to get to quickly with pathogens. And Barry, thank you for bringing up MAC infection, because I think that MAC infection is a really wonderful, it's a really good example of the issue. So MAC stands for Mycobacterium avium complex, and it's a family of bacteria that often infect people that live in sort of rural areas or are exposed to sort of dust and dirt and farms and soil. And, something that is fairly obvious for most people to hear from me is that I grew up in sort of Western Australia, which is quite a rural area. There's lots of farms and so on and so forth. Something that some people might not know about me is that, clinically, when I was working in Australia before I came to be a scientist in the United States, I used to work in a critical care respiratory ward, and we used to see people who were showing up with severe lung disease. And often, because Western Australia was such a rural location, people with MAC infection would occasionally end up on our ward to receive assessment and treatment. Now, people get infected with Mycobacterium avium complex bacteria early in their life. So 20s, sometimes even earlier than that, in their teens. And then these bacteria stay latent in the bottom of your lung for 40 or 50 years before, as an older adult, your immune system starts to falter a little and they start to cause irritation. Now, most people with MAC infection honestly can survive it. I'm not going to say it's pleasant, because it isn't pleasant. You have a chronic cough. You often have a fever. You often lose weight. You often have sleep disturbance, and all of those things lead to a miserable, quality of life as a result of not sleeping and just feeling like you're coughing all the time, and so on and so forth. But the point is, it's not a fatal infection in most cases. It just sort of persists within you. You can't test your blood for MAC infection. It won't show up, even though you have a symptomatic bacterial infection. MAC infection won't show up. In fact, what they need to typically do to diagnose MAC infection is what's called an induced sputum, meaning sputum is just a fancy medical term for phlegm that you cough up when you're sick. The thing about MAC infection is you don't even cough up phlegm most of the time. You usually cough up clear fluids. So they need to do something called an induced sputum, where they flood your lungs with hypertonic saline solution, a heavy saline solution. It causes you to cough quite a lot. You cough up things from deep within your lungs, and they go and they biopsy that, and they'll find evidence of MAC infection. The treatment for MAC infection unequivocally is low-dose antibiotics over a long period of time, often a combination of antibiotics over a long period of time, in order to take out the bacterial infection. And as I've seen mentioned in the chat, it's not necessarily something that a lot of doctors know how to identify or even treat, because yeah, you're coughing like you have a lung infection, but you're not coughing up phlegm. Your blood tests are fine. Often we will hear a lot of people getting diagnosed with a neurogenic cough or a psychogenic cough rather than the MAC infection itself, which is just distressing and, you know, very upsetting for a patient to hear when they're coming to you saying, I have been coughing nonstop for the last 2 years. My family are concerned and, you know, frankly annoyed by it, and, you know, what do I do? So you know, it's a very real and serious condition that can very much affect quality of life, and we just don't see it. It's invisible to us unless we do some very invasive testing. The link between MAC and long COVID is really interesting. The thing that we've, you know, and I can't directly answer your question, Barry, because no one has actually published any work on this. I think it's a very interesting topic. However, indirectly, I can answer the question in that it makes a lot of sense that that people who had an underlying MAC infection that had not yet manifested would manifest after COVID and getting long COVID. As you know, as myself and my wonderful colleague Akiko Iwasaki, as we published in 2023, folks with long COVID frequently experience T-cell exhaustion. They frequently experience reactivation of latent pathogens as a result of that immune system exhaustion. And so it makes a ton of sense that something that was always going to unmask and manifest itself as your immune system got a little weaker or got a little more tired from fighting off other things would manifest early as a result of SARS-CoV-2 infection. So the short answer to the long ramble that I just went on is that the MAC infection was always with you, and the SARS-CoV-2 infection unmasked it. And now, you know, Katie and Barry, you know, the recommendation is low dose antibiotics for a long period of time. You know, a skilled pulmonologist, which is not me, will obviously be able to recommend that. But I strongly recommend finding a pulmonologist who's experienced with MAC infection who can prescribe the antibiotics, because inhalers and steroids are not going to get it done. You need the antibiotics to kill off the MAC infection. And I'm always a big fan of supporting, you know, patients forming support groups of special interests like this, because this is how you get physicians to gain expertise in these sorts of things. Because you form a patient group that's large enough to say, hey, there's a lot of us here and we're really struggling. You need to learn what's going on.
Thank you. And so we are coming up on 3 o'clock, and I want to do a quick scan of the chat and just make sure that we didn't miss any questions. I think we pretty much covered everything. And sorry, my dog is deciding to try to burrow into the hardwood floor. Please stop. Okay. So yes, let's recap and talk about some of the things that we've covered. So we talked about pathogens being disease-causing organisms that live in our bodies. And if our bodies encounter a disturbance where our immune system is distracted or is hampered, or if our body is distracted trying to do other things than what it would normally do, that could present an opportunity for pathogens to actually cause disease in our bodies. And so that could be a reason why people are experiencing chronic illness. And what makes it complex is that we don't know all of the different manifestations. We don't have yet the testing that we can identify where these organisms or viruses are persisting in our bodies. And it's a lot of this knowledge is still in development. And so I want to touch on, before we head out, what are we doing at CoRE? What research are we supporting? What are we looking at? And also at Polybio, Amy, what knowledge are we looking to develop and what's in progress here? And
yeah, it's a huge focus of both Polybio's program and CoRE. Everything from just better iterating the technologies to be able to find, like I said, smaller amounts of pathogen genetic material inside host cells, small amounts of protein that might leak into fluids from pathogens in tissue, or actually the methods to really be able to find any fungal, viral, bacterial infection in tissue via some method like metatranscriptomics. We have many groups working on this. Then in terms of CoRE and treatment, we're running several clinical trials that are just going in a direction of trying to test even actually generic and widely available therapeutics to see if we can address some of these infections with them. For example, Truvada, we're trialing Maraviroc. We may trial rapamycin. I can explain that one in another episode. I actually think that taken in a low dose, it might have some control on helping the immune system address infections, a whole other topic. So basically our goal is to improve the testing via research, use CoRE as a place where we can, when something works, bring it into the clinical setting, right? In other words, we're the place where we can do that translation from the research lab into the clinic. That's part of why we created CoRE. And then also just start trials so we understand the better arsenal of therapeutics that we have to be able to knock down these pathogens or contain them better.
I think it's also worth mentioning that we're also running some clinical trials right now to better understand how people with one diagnosis, such as long COVID, may also have co-infections with things like Bartonella and Babesia and tick and vector-borne illness, as well as other, latent viral reactivations, just so that we can actually catalog this and report this out in the literature. It's like, people who had an illness that was triggered by a SARS-CoV-2 infection also have evidence of infection with other pathogens. The other thing that we're working on in addition to that is also, Amy mentioned a bunch of larger triggers and larger hits that can cause the immune system to, sort of waver and experience worsening of co-infection. We also have a number of trials where we're just trying to understand how, cyclical hits can have an effect, such as in people who menstruate, looking at the hormones of menstruation and trying to understand at what points are symptoms at their peak during menstruation, and how does that correlate with hormonal balance, and is there something that we can do about that to stabilize some of the symptoms that people are experiencing, as a result of menstruation, like bioidentical progesterone use or testosterone supplementation or peptide use. These are things that are available. These are things that are, practical, so long as we can understand the relationship between some of these cyclical, immune and hormonal changes that occur and how they influence the body.
Amazing. Well, thank you both. Thank you to, right now we have 1,058 people watching us. So thank you to everyone who is tuned in. I hope that this was helpful, informative, and intriguing. So please catch us next month. We do this once monthly. We will be speaking on a different topic in regards to roots and drivers of complex chronic illness. So thank you all. Have a great day. Bye.
Thank you.
Thanks, everyone.
Bye, everyone.
Bye.